A scientist is inventing bulbs that last longer. Can we help him in data visualization? Stick around to find out. Before helping him, we need to learn about statistics, bar graphs, histograms of type 1, histograms of type 2, and frequency polygons. Suppose a class teacher wants to study data of students' birth months. She wants to find out how many students were born in November and which month were maximum number of students born in, etc. We can visualize this on something like a 2D Cartesian coordinate system. On the x-axis we can plot months. On the y-axis we can plot number of students born in that month. For example, we can draw a bar of length 3 units since 3 students in the class were born in January. Bar of length 4 for February since 4 students in the class were born in February. Similarly for other months also. Now, looking at this bar graph, the class teacher can answer the above questions. We can see 4 students were born in November and the maximum number of students were born in the month of August. As a second example for using bar graphs, let's look at what are the expenses of a family in various areas. Family spends 4,000 rupees on grocery. Note the table says 4 because unit of spend is 1,000 rupees. Similarly, rent is 5,000 rupees or 5 units, spend on education is 5,000 rupees or 5 units, spend on medicine is 2,000 rupees or 2 units, and so on. This data can be plotted on a bar graph with areas along the x-axis and expenditure along the y-axis. A bar 4 units high shows the spend on grocery. A bar of length 5 units shows the rent and education spends, and so on. Next, let's look at histograms. These are like bar graphs, but the data is continuous, not discrete. What that means, previous example dealt with x-axis variables like grocery, rent, education, etc. These are discrete, separate from each other. However, value of weight of a student is a decimal number which is continuous on the number line. Weight ranges are continuous, 30.5 to 35.5 and continuing with 35.5 to 40.5 and so on. We can see 15 students fall in the range of 40.5 to 45.5 kg range. Note, no student has weight between 0.5 to 5.5 kgs or 5.5 to 10.5 kgs. So we did not show it on the number line. Instead, we use a shape called kink or a break to indicate that x-axis data is not starting from 0. On x-axis we start from 30.5 kgs and on y-axis we have number of students. 9 students fall under 30.5 to 35.5 kg range. 6 students fall under 35.5 to 40.5 kgs range. 15 students fall under 40.5 to 45.5 kg range, and so on. Note, 1 unit on x-axis is 5 kgs. Also note, area of the bar represents number of students falling in that category. For example, area of the highlighted bar is 1 unit breadth times 15 in length, giving us 15 students falling in 40.5 to 45.5 kgs range. Also note that the bars are touching each other without any gaps between them, as x variable weight is continuous. Till now, width of all the intervals on x-axis are same. For example, 1 unit on x-axis is 5 kgs in this example. What happens if the intervals on the x-axis are of different width? Let us look at an example where we can get it wrong and then we'll show you how to correct it. Here we have a data of range of marks and the number of students scoring those marks in those ranges. But the first range is 0 to 20, which is 20 marks, which is 2 units in width. And the last range, 70 to 100, is 30 marks, which is 3 units in width. Now, if we plot a bar according to the given length in the table for 0 to 20 range, we have 2 units breadth and 7 units length. But area now is 2 into 7, that is 14 students, which is wrong, because it's only 7 students in that range. Similarly, if bar length for 70 to 100 range is plotted as 8, we have 3 units for width and 8 units for length. That gives us area which amounts to 24 and which shows it is 24 students in that range, which is again wrong. Okay, now let us see how to fix this. When we have x-axis ranges that have different unit widths, we have to calculate two more columns in the table. One for width of the range and another for actual length of the bar to be plotted in the graph. We have to calculate actual length is equal to number of students multiplied by width per unit divided by width of the range. For example, for the first range, the actual length is equal to number of students, which is 7, multiplied by width per unit, which is 10, divided by the range width, which is 20. So 7 into 10 divided by 20, the actual length is 3.5. Similarly, for the last range, the actual length is 8 multiplied by 10 divided by 30, which is 2.67. For other ranges, the range width is the same as width per unit, which is 10 marks, so the lengths are as before, which are correct. Only for the first and last range we have to change it because the width of the range are different. Now let us look at what frequency polygon is. If we consider the previous histogram of weights and plot midpoints at the top of each of the bars and starting and ending points on the x-axis, and we join these points by lines, we get our frequency polygon, which is shown in orange color. This is another way to visualize data. Let's take another example where we can draw just the frequency polygon without the histogram. Let us say we have for various cities cost of living ranges on the x-axis and number of days spent on the city on y-axis. As shown in the table, we can have a midpoint column which has value of midpoint for each of the ranges. For example, midpoint of 140 to 150 range is 140 plus 150 by 2, which is 145. Similarly, for 150 to 160 range, it is 155 and so on. We can plot midpoint values along x-axis and number of weeks along the y-axis as the 2D points on the 2D Cartesian coordinate system. So we can plot 145, 5, 155, 10, 165, 20 and so on in the coordinate system and join these points by lines to get the frequency polygon. So with this knowledge under our belt, we can help our scientists making the bulbs. If we look at lifetime of bulbs in hours, it falls in various ranges. The table also gives the number of lamps in each range. When we plot it as a histogram, lifetime in hours along x-axis and number of lamps along the y-axis, we can see most lamps had a lifetime in the range of 600 to 700 hours. So the scientist can quote this lifetime when the bulbs are sold to customers. So this is how we have helped the scientists calculate and predict the average lifetime of the bulbs, which is 600 to 700 hours. Hope you had fun learning about graphs and histogram, friends. We have thoroughly studied, digested, thought about and simplified the concepts for you. So please like, share and subscribe.